Basically, the calculation is an application of the residue theorem, because now we have an integral of a complex function. There are two integrals, but actually there is only one integral. You see, the integrand only depends on the difference. So it's true that there are two integrals, but that's precisely why we introduced this switch function. Otherwise, the result is infinite, because we are calculating the probability that this event happens from the infinite past to the infinite future. So unless we have this switch, it won't give anything meaningful. But normally, as you may be familiar with in quantum mechanics, what you compute is not the probability, it's the probability per unit time. So there is a factorization of the time, omega, which means that out of these two integrals, one integral remains over the difference. But the other integral is the one that gives, it would give infinite, but the integral of the function c of tau, because that's omega, because c of tau is... So what we do is as follows. So we have two integrals here, and they reduce to the integral on tau minus tau prime, the difference, and an infinite factor. But also the integral on tau minus tau prime is limited because of the switch cutoff. However, remember, we want to take omega to infinity. So basically what we get is, let me see how I call it, u. Now u is tau minus tau prime. So there is a factor omega, which is one of the two integrals factorizing an infinite factor. But in the other integral, we can take the limit omega going to infinity. Because this integral will be meaningful, we will be able to do it by means of the residue theorem. And we do not need anything else. So we have v squared u squared minus u plus I epsilon squared. So that's the integral we want to do. We want to compute. And I forgot. So now we compute this integral by means of the residue theorem. And we will find that the result is 0. Where are the poles? Well, so now u is tau minus tau prime. The poles. The poles are when this is 0, so you have plus or minus Vu equals u plus I epsilon. So u is our complex variable. And let's see where the poles are located. So I move this to the right hand side. So I find u minus plus Vu equals minus I epsilon. So that is 1 minus plus V times u, which means that u is equal to minus I epsilon divide by 1 minus plus v. The important thing is that epsilon is positive, and 1 minus v or 1 plus v is positive because the velocity cannot exceed the velocity of light. And so these two poles have negative imaginary parts. So we are in business if we can close the contour on the upper half plane. So we are calculating here, that's the integral we want to compute. If we can add at no cost the arc at infinity in the upper half plane, we get 0 because of the residue theorem. And we can, because you see that you have this exponential here, but in the upper half plane, where, so here, the exponential e to the I ei minus e0 u is decreasing because ei is certainly greater than e0 because that's an excited state. So e0 is the lowest energy level, the ground state, and u is equal in the upper half plane x plus I y with y bigger than 0. So the imaginary part of u is bigger than 0. So you have e to the I ei minus e0 u, that is equal to e to the minus y ei minus e0. So the modulus. And so it decreases exponentially in the upper half plane. You close the contour there and you get 0. And that's because we chose the retarded potentials, not the advanced potentials. They would have had two poles there, and not the Feynman prescription, because with the Feynman prescription you would have had 1 and 1. Fine, that's good, but now we can move to the more interesting part, which is the hyperbolic motion. Which you certainly know from some relativity course, special relativity. Let me describe what it is. Well, by giving formulas already. The trajectory. I give you the trajectory and then we check that it is the correct. We cannot make the entire derivation here, otherwise it would take too long. So that's 1 over g hyperbolic sine of g tau. Tau is the proper time, remember. G is some acceleration. Now it's a constant, but it is the acceleration. And x is very similar with the hyperbolic cosine. Okay? In particular, you know that t squared minus x squared is 1 over g squared times hyperbolic sine squared minus hyperbolic cosine squared, that's minus 1, that's a constant, which is why it is called hyperbolic motion. This is a hyperbole. Let's compute a few properties such as the velocity, the acceleration, to check that the acceleration is in some sense constant. So the x over the t is equal to what? Dx is, one thing to make the calculation easier. Let's differentiate this equation, and you have 2t dt equals 2x dx. Differentiate. So dx over dt is equal dx over dt to t divided by x, by the same formula, and that's the hyperbolic tangent so if we want to write this, we have 1, the hyperbolic tangent, zero, 0. 1 because dt over dt, this 0 component is 1. But we want to compute the 4 velocity and the 4 acceleration, the covariant one. So dx mu over d tau is equal to this thing times dt over d tau. And we know what dt over d tau is, because that is the hyperbolic cosine, and g simplifies, so that's just the hyperbolic cosine. And so we just multiply this by the hyperbolic cosine, which means that we get hyperbolic cosine, hyperbolic sine 0, 0. Normally this is called u mu. So let's use that notation. And you notice that u mu is equal to 1. Because that's hyperbolic cosine squared minus hyperbolic sine squared. Finally, the acceleration for vector is the derivative of x mu with respect to tau, and that we can compute quite easily. The derivative brings out a cosine, and for the rest we have hyperbolic sine, hyperbolic cosine, 0, 0, which implies this identity, that the 4 vector squared is constant. And the constant is the acceleration squared. Now, we have to compute this thing here. And we have to do it. There is little we can do it. We can do. So we need to compute it, and that's not the difficult part. That's straightforward. The annoying part is this, basically, how to treat this I epsilon. But apart from that, it's just hyperbolic cosines and hyperbolic sines. But there is a trick, some annoying part there. So we have to compute this. So let's do it. Let's start from the space part. X is 1 over g cosine, hyperbolic cosine, so we have a 1 over g squared, and then here we will have a hyperbolic cosine minus hyperbolic cosine squared. Minus the same thing. It's better to collect a factor g and redefine epsilon. Epsilon is positive. Doesn't matter if we redefine it by means of a positive factor. So we have hyperbolic sine of g tau prime minus hyperbolic sine of g tau minus I epsilon. Okay, now we have to evaluate the squares, so let's collect 1 over g squared, epsilon bar. Let's collect 1 over g squared. So we will have 1 cosine of g tau prime squared minus a sine squared, that will give 1, from the square of this and this. From the square of that and that, we will have another 1. So that's a 2. Then we have a double product there, 2 cosine h g tau prime cosine, hyperbolic cosine g tau. And there you have minus minus, so plus 2 sine g tau prime sine g tau. And we have computed everything but one thing, the terms with epsilon bar. Well, those terms are only interesting in the linear part, because epsilon bar squared, epsilon has to go to 0. So the prescription is given by epsilon bar, the terms that are linear. And we have minus, so 2i epsilon bar plus sin h g tau prime minus sin g tau. And we can neglect the terms. Yes. So yeah, there is also one thing we can collect, that's a factor 2. Let's see how we can simplify this a little bit. Two divided by g squared, then there is 1 minus cosine minus sine is cosine of the difference. hyperbolic cosine of the difference. You can check it with the exponential representation of the sine, hyperbolic sine, cosine. And then we have that last part, and the last part we just copy. Okay. The last part we just copy. Plus I epsilon bar hyperbolic sine g tau prime hyperbolic sine g tau. Remember that these steps I'm calculating you won't find in textbooks. They will just jump to the result, and who knows how they get there. Well, they get there this way, but if they don't tell you, it might be. This you can find in Birrell Davis. That's a book, but it won't be derived, so it's just thrown there, and don't think it's particularly useful. Another way to write this, another formula, 1 minus cosine, is a sine squared of half of the argument. So hyperbolic sine squared of g tau prime minus tau divided by 2. And well, it's the usual formula for the sines. So now it's hyperbolic sine, but you know that twice the cosine minus 1, twice cosine of the cosine of the twice the angle minus 1 is related to the sines and cosines of half an angle. And 1, and also if you have a plus, so you have just to check the signs, the sines and the sine or cosine there. And the rest, the rest we copy. Well, finally, this is equal to, but this we will check because it's not totally straightforward. This is equal to to minus 4 divided by g squared hyperbolic sine squared of g tau prime minus tau minus I epsilon, some new epsilon, divided by 2. How do we prove that? So we have to find a certain epsilon tilde which is related to epsilon. It can be a relation that depends on tau and tau prime, but the only thing you need is that epsilon tilde must go to 0 when epsilon bar goes to 0, and epsilon tilde must always be positive, strictly positive. And how to show that this is this will make the final formula will make our calculation rather easy, more or less. So we just expand the second, this one, in epsilon to the first order and check that it is equivalent to the first expression, this expression, up to a redefinition of epsilon. So you have minus 4 divided by g squared times hyperbolic sine of g tau prime minus tau divided by 2 plus epsilon tilde times the derivative of that function calculated in 0, where the function is this one. So we calculate that derivative and then we compare that part we want with that, which is this one, with this one. We check basically that the ratio between the coefficients of epsilon bar and the coefficients of epsilon tilde is always positive, strictly positive. That's what we need to do. So let us calculate this derivative in 0. And that is minus 4 divided by g squared. Then there is a 2. There is a hyperbolic sine. And then there is a derivative of the hyperbolic sine, which is a hyperbolic cosine. And then we have to multiply this by the derivative of the argument with respect to epsilon tilde, which gives minus ig over 2. Okay, what is this? So minus and minus go away, 2 and 2 go away, 1g and 1g go away. So you have a factor I, a factor 2 in front, 2i, and instead of 4 I write 2 because then you see you have twice sine times cosine. That's the sine of twice the angle. It's not an angle, but whatever. Good. Times, yes. So we just need to show that the ratio between this and that is positive, always. The ratio between this and that. Let's say, well, g squared is positive, so I don't care about g squared. This and that, which is true, of course. And that means that we just need to show that hyperbolic sine of x minus the hyperbolic sine of y divided by the hyperbolic sine of x minus y strictly positive for every x and y. And should have a minimum actually, different from 0, otherwise it could be, yes. So how to do that? Let us define A equal to e to the x, B equals e to the y. So I repeat, we want to show that the relation between these two is always positive. X and y are g tau prime and g tau. G tau prime and g tau. If you want, you can write it. X is g tau prime, y is g tau. Hyperbolic sign is a minus 1 over a. That's the hyperbolic sign of x. A e to the x divided by 2, but the division by 2 is up and down, so minus b plus 1 over b. And what is the hyperbolic sign of x minus y? Is a divided by b minus b divided by a. Observe that a is always positive, b is always positive, x yes. Now, if you compute this, let's just multiply by whatever, a times b. So you have a squared b minus b minus b squared a plus a, multiplied by ab both. Both the numerator and the denominator factorize in a minus b. And the numerator indeed is a minus b times 1 plus ab. Why? If you multiply, you have a times 1, a, minus b times 1, a times ab, a squared b, minus b times ab, b squared a. So now you see that the result is always positive. In the end, we can write our formula by means of this, which goes into the denominator. And again, it will be possible to compute it by means of the residue theorem, with the difference that there are now infinitely many poles, but there is a way to handle that. A little bit of patience, I will do it. So basically we have this, and then 1 divided by this thing here. So there is a minus 4 over g squared, which will become a minus g squared over 4 times 1 divided by hyperbolic sine squared g tau prime minus tau divided by 2 minus I epsilon bar. That's crucial, because otherwise we don't know how to calculate. With the residue theorem, again, we see that the integrand depends only on tau minus tau prime, and so we will have one integral only and a factor omega in front. Let's see if we can finish it today. I don't think we can finish it today, so we will continue tomorrow a little bit. Anyway, minus g squared omega. Now there is 16 pi squared, so 4 pi squared. And then again, u will be tau minus tau prime. This factor in front is always the same. So we have the integral on du from minus infinity to plus infinity, e to the I, and the integral now is this, e to the I, ei minus e0 u divided hyperbolic sine squared of g tau minus tau prime, u, tau prime minus tau, actually. So it's crucial. It's tau prime minus tau, so this is minus u. There is a square, so it's like saying u plus I epsilon tilde divided by 2. Okay. Now, how to compute this by means of the residue theorem? You have to work out the poles of that. But there is an identity that rescues us. The identity says the following thing: 1 divided by the hyperbolic sine squared of something, which we will write as pi y. So y will be g divided by 2 pi u plus I epsilon tilde. That is equal to 1 divided by pi squared sum for k that goes from minus infinity to plus infinity of 1 divided by y plus I k squared. The sum tells you where the poles are, and you have to sum the residues from every pole. Actually, these are double poles, but you can use the formula for the double poles. So if you have a complex function of z, the nth derivative, an analytic function, in z is n factorial divided by 2 pi I. Then you have a contour integral of f of zeta d zeta divided by zeta minus z to the power n plus 1. So some contour that contains z. So these are double poles, but it's not something particularly scary. So we will do a change of variables, because now the variable will be y. So what is dy? That is g divided by 2 pi du. And then we will have to compute the poles. The poles are y equal minus ik. And that means that this is g divided by 2 pi u minus plus I epsilon tilde. So that means that u is equal to minus I epsilon tilde minus I k 2 pi divided by g, where k is an integer number, positive or negative. And so if you plot them as before in the u plane, u complex plane, and you know as before that you can close the contour in the upper half plane because of the exponential there for every term of the sum, so you will have to exchange the sum and the integral. The point is that you have these poles that they are all on the imaginary axis, and you have them everywhere. But if you apply the residue theorem, you will have only to consider those that are in the upper half plane, which are those with so epsilon tilde is very small, so the sum restricts to k equal negative. Yes. Because if k is negative, then you pick those poles. So we will have to compute half the sum only for negative k and tomorrow, and magically we will find the black body spectrum. Okay, so we end the derivation tomorrow.